All right, now we're going to do an example applying Kc to an ice table. This is crucial stuff, people, so follow along, make sure it makes sense, and that you can do it on your own. So I'm going to say that 3 moles of carbon monoxide is placed in a 500 milliliter vessel that already has 3 moles of water vapor, right? And we allow the following equilibrium to be established. Okay, so that's just the reaction equation, the equilibrium system, and I've included a value of Kc. Okay, I'm going to show you what we do to determine equilibrium concentrations of each entity. So that's everything we see here, all four. I underlined concentrations. I've mentioned we can use concentrations in ice tables, and we're going to have to do it this time. Okay, so what I've done is I've rewritten the equilibrium system. It's going to go in an ice table. All right, but there's lots of work to do. The ice table this time we're going to use concentrations. We have the initial amounts of these guys, 3 moles, right? 3 moles of each of them. We also know the volume that they're contained in, so we can get that concentration. So I'll just do that over here. Carbon monoxide concentration was 3 moles. 500 milliliters is equal to half a liter, so that's 6 moles per liter. Okay, the water was the same amount in the same container, so it's the same as well, 6 moles per liter. That's what we're going to put in here. Okay. We assume that these guys started with nothing, so their concentrations are 0. We don't know any of these, which seems like a bit of a problem. I'm going to show you exactly how we get it. What we do is we assume that one of these changes by an amount that I'm going to call x. I'll just start on the right. You apply your molar ratio to that. Now I've started simple. All coefficients are 1, so that means this change is going to be plus x. These guys are going to go down by that same value because, again, the molar ratio 1, 1, 1, 1. Okay, the equilibrium concentration is now going to be 6 minus x for these guys, and these guys are going to be x. Now we have to find out what x is, and we do it with Kc. Okay, so let's write our Kc expression. Remember, you start with the products. Everything here is a gas. There's not going to be anything tricky going on. Multiply the concentrations of the products. There's no exponents because every coefficient is 1. Divide by the concentration of the reactants. Okay, and we know that it equals 4.2. That was given to us. All right. Let's see. These guys are x, so that's going to be x times x. These guys are going to be 6 minus x. All right, so we have some math to solve. I'm going to flip the page and we're going to do that. Remember, we had x times x. That's x squared. We had 6 minus x times itself, so that's 6 minus x squared. This has to equal 4.2. All right. Check this out. In Chemistry 30, it says right in the curriculum, you never have to solve quadratics unless it's simple. You never have to use the quadratic equation, I should say. All right. This one's going to be real easy. If we take the square root of both sides, we get rid of those exponents. Oops, excuse me. My goodness, getting excited. So I'm going to get x over 6 minus x equals the square root of 4.2. Let's find out what that is. All right, and this is an equation that we can all solve. So I'm just quietly doing the steps. I hope nothing's controversial here. I'll explain myself a little bit. So I expanded the 2.05, multiplying by 6, I got this. Okay, subtract it times x. Now I'm bringing this term over here. These guys get together. And then divide. Okay, I get 4.03. That's what x equals. Maybe we've forgotten. What on earth is x? That's these guys. We have to subtract that from 6 to get these guys' concentrations. Okay, so I'm going to summarize my answer here, flipping back and forth. This answer, this was our H2 concentration. What else? Carbon dioxide. All right. The other guys, carbon monoxide and water, it's 6 minus that. Okay. I think you're going to get 1.97 moles per liter. Okay. This is a big skill that you're going to need for this unit, going from Kc to equilibrium concentrations.